So we have this cheap electric dirt bike. I think it's 500 watts or something that the kids play around with. It's got 3 different speed settings and it's been a fun toy. But the lead acid batteries, they are done. So let's open it up and see what it ate. We have 3 lead acid batteries, 9 amp hours. We have the motor there. I think it's 500 watts, I don't know. Let's see how many. Here are the motor cables. 2 motor cables, means it's a brushed DC motor. And here we have the controller. Doesn't seem to be fastened really well. So I'll take some dimensions and figure out what kind of battery pack we could fit there. I'm gonna go with LiPo 4 chemistry. It's a safer chemistry to avoid fires and stuff. And I've been looking at this 32700. It's 32 millimeters times 70 millimeters. So let's draw up the battery pack. I'm using NanoCAD. It's a free 2D modeling software. We have the base of the battery, footprint, and then we have the height of the battery. Oops. Let's see. The base was 150 times 135 and the height was 190. Yes. And we know a battery is 32 millimeters. You can spread that out. Like that. And we make it from the other view also. Like this. So if we have the cells lying down, how many can we fit this way? We can only get 1 row of cells. That's no good. Let's check it the other way. Almost. But we will have nickel and the BMS, so that's not really possible to get them in this way, else it would have been perfect. Let's check it like this. Okay, this could work. Let's see. Yeah. So I think this will be the battery pack. It will be a double decker. We have 12 cells per level, 24 cells. It will be 2 parallel cells and 12 in series. So it will be a straight fit for the 3 lead acids that's there currently. So now we get to work.
So here's my workflow with batteries. First I charge them up in the charger fully. Afterwards I do a discharge test. I take note of the measured capacity and then I process all the capacities on a website named Repacker.
So here I have entered all the capacities that I measured. I want 12 cells in series and 2 in parallel. So this site then tries to balance all the cells as equally as possible. So I can just print this out and use it as help when I assemble the pack. So I start with gathering all the stuff I need for the build, and I also drew up and 3D printed some cell holders. One important thing to add are these insulator rings on the positive end, so that the nickel strip doesn't wear through the plastic sleeve and get contact with the rest of the cell, because that would short circuit the cell. With the cells in order, it's time to take out the spot welding gear. I have this Sanko 709 AD. It's European version, so it's 220 volts AC. I think it's a decent machine, but I would really need to change the cables to bigger ones and maybe make some better welding tips for it. So the first layer of nickel I'm laying down is the serial strips. I'm using 2 strips, 7 times 0.2 millimeter pure nickel, and they are rated for about 5 amps each. So the first layer will give a continuous current rating of 20 amps. That's 2 strips per cell, 2 parallel cells times 5 amps. By using 2 strips and welding with 1 tip on each, I can force down the welds through the battery and get a good connection, even though 0.2 millimeter nickel is pushing the limits of my Sanko. One problem with this battery layout is that in this one spot I only have half the amount of serial strips. I did a sketchy thing and pre-soldered a pair of 2.5 square millimeter fine stranded copper wires to some 25 millimeter nickel. In my theoretical world, the first layer of nickel is good for 10 amps, the second layer 14 amps, and the 2 copper wires around 30 amps each, so that would be 80 amps in total. But theory and real world aren't always the same thing, and the cells are only rated for 30 amps continuous each, so I figure it will be okay for this 500 watt motor. I cut some nickel strips and took help of soldering plugs to attach the BMS wires. This way I don't have to solder straight on top of the cells. I marked each strip with numbers to assure I get everything connected right later. To avoid having different polarities sticking out of the sides, I put on some shrink tubing and then proceeded with the job. After finishing the first layer of strips that will be folded, I used a ruler to give them a slight bend. The reasoning here is that the first layer needs to be a bit longer than the second layer. I noticed afterwards that the strips are a bit on the longer side and should have been shorter, but maybe next time. At this stage I'm welding on all BMS wires that will be on the folded side. I did some unscientific tests with a blowtorch and a heat camera, and I came to the conclusion that this plastic sheet deforms at about 100 degrees Celsius. The cell holders are printed in ASA material, so they will soften already at 90 degrees. But I don't see this as a risk, as this battery pack will never be run that hot. Folding the battery is nerve-wracking, as even if the cells are almost empty in my case, they still hold a lot of energy, and they will send sparks flying if anything shorts. I luckily made it with all my fingers intact and without any fires. At The battery is folded with a sheet of padded plastic between. I printed some small attachments to keep everything together. The BMS wires were a pain to sort out and quite time consuming. I fiddled a long time and even redid them once, but still came out ashamed of how it turned out. As it's time to attach the BMS, I start with soldering the main leads onto some nickel strips. While I'm at it, I'm changing the connector types to XT60 on the dirt bike so that I can use an anti-spark version on the battery pack. It sure looks like a mess at this point, but we will soon have it covered up with heat shrink. I have heat shrink in a few different sizes, and that really helps to tidy up things. As this is a seasonal vehicle, I'm keeping the BMS on the outside so that I have access to unplugging the sense wires. If you leave a battery with a BMS connected for the winter, there's a risk that the BMS drains the battery over time. With the battery done, it's time to install it back in the bike. I had to get rid of the old battery holders and some other junk in the way. I also 3D printed a bottom plate that I added some padding on. The old fuse will not break a short circuit without setting things on fire, so I made a new fused adapter between the battery and the controller. Fixing the battery to the bike escalated quickly into a temporary permanent solution, where I used old bike inner tires that I tensioned to keep it in place. Not really a solution I'm proud of, but we will see how it holds up. I finished this build in August last year, and now it's already February, so by the time I got around to making this video, I had lost all the drive action videos. But here's some winter footage instead. The power of the bike is still the same as before, so the upgrade isn't really noticeable there, but the big improvement is range. With the old batteries, the kids were able to drive around our track for 10 to 15 laps, but now afterwards I counted 50 laps or so, and the kids run out of capacity before the batteries. The batteries costed me about 85 euros and maybe 15 euros total for the other bits I used, for a sum of around 100 euros. I'm happy with the result, and the kids are even happier.